Hello everyone. My name is Yadu. I'm the lead developer for Parsl, and I'll be diving straight into a notebook that will show you how to plug an execution system into Parsl. So when I say that, what do I mean by an execution system? So I'm saying this very broadly, but any system that can take some Python code or some bash command lines and execute it on whatever compute system. So a laptop or a GPU cluster or some exotic cluster of Raspberry Pis, I would call that an execution system. So the first question is like, why would you want to plug an execution system into Parsl? So there are a couple of good reasons. So you might have an execution system that executes some code on some exotic system that we don't support. So for example, if you might have a specific flavor of GPU cluster that you have, which we don't really support. And if you have a system that gets stuff running there, you could plug that into Parsl instead of making Parsl do extra work. Or you might have an execution system that simply is either faster or has more reliability or even better, like more efficient task execution, right? So you might want to get those features by plugging that execution system into Parsl. Or you might want to mix and match existing capabilities in Parsl with systems that you already have. So those are the reasons why you might want to do this, right? So in this notebook, what I'm going to cover is I will cover the Parsl executor API. I will give you a very brief overview of Balsam, which is the execution system that I'm going to integrate into Parsl. And I'll cover very quickly like some basic operations that how we can do that with Parsl, with Balsam from a Python interface. And at the end of it, we'll write a Balsam executor for Parsl from scratch, pretty much, and we'll test it. So I need to be quick about the first bits, so I'll try to go along fast. So first things first, this Jupyter notebook is running at ALCF. That's the Argonne Leadership Computing Facility. So because it's running there, this notebook actually has access to the COBOL scheduler. So I can run stuff and talk to the COBOL scheduler directly from this notebook. This notebook already is in an environment where both Parsl and Balsam libraries are available in the Conda environment it is running in. And I'm going to try and focus on the interfaces and less on the specifics of the code. Okay, so the first bit is the Parsl executor. So I would say that the Parsl executors basically are extend on and build on the concurrent futures executor class. So it's a standard library in Python, and that is what we've taken and extended on. So if you have something that conforms to the concurrent futures executor class, it will plug into Parsl easily. So this basically gives us a very standard interface, very common in pretty much all of Python ecosystem, that at its core is very simple. So there is also a bit of a discussion that I could get into about features, but I'm going to skip that because Ben talked at length about features. Please go and maybe listen to his talk from yesterday. There's already material from that posted online if you want to know more about features. So the key bit that I want to talk about is this bit. Can people see my pointer? I'm hoping that you can. So in Parsl, the data flow kernel keeps track of whatever your workflow is doing, like all the dependencies and all the other bits and pieces. When it comes to executing stuff, it talks to an executor, like as its name says, it will execute your functions for you. So there is a submit method that an executor must have. So it takes a Python function, its parameters, takes it off and ships it off to execute, and it will give you a future back which will track its execution asynchronously. Now, there are a bit of other methods that are inside, but those are less relevant. So there is a scale out, scale in, and shutdown, a few other pieces that we can just ignore for now. So this bit is going to be the core piece that we are going to focus on in this demo tutorial. Right? Okay, so the piece that we are trying to integrate into the system. So that's Balsam. So Balsam is a HPC workflows and edge computing system out of ALCF. So it's an execution model that follows the pilot job model, where Balsam will talk to the scheduler, get a bunch of nodes, and it will fill it with workers, which will pull from a database and do a lot of tasks. So this system is designed to be very robust. It is very well supported across all of ALCF, all of the machines at ALCF. And it's pretty robust and reliable to run stuff over Balsam. So that's what we're going to be integrating with. So first things first, let's make sure Balsam and Parsl are available in this notebook, and it's all up to the latest versions. Okay, so Balsam is at 3.2, 3.8, which is the latest version, and Parsl is at version 1.0. Now, the first step that we want Balsam to do for us. So the first few steps are going to be all interactions from Balsam that we need. I'm not going to focus so much on the specifics within this, but I want to basically point out at the key functionality that we are getting from Balsam. So the first bit is we need to have Balsam talk to Cobalt, which is a scheduler for Theta supercomputer, and get us an allocation, a job running, which will get us a bunch of compute nodes to run our functions on. So this Balsam submit batch job, it's a very, very thin Python function that internally calls to the submit launch method in Balsam. So you can basically treat this method, Balsam submit batch job, as if it is talking to Balsam, so that Balsam will go and get you some resources from Cobalt. Okay? So let's just activate this, activate that. Okay. So next bit is slightly more involved, and I think I should get into the details of this. So we need to register an application with Balsam. Think of it like this. Before you run a function, you need to define the function. So similarly, Balsam has this notion of an application definition that you need to specify and register with Balsam. So what we are going to define is, I'm going to name it execute Parsl task. I'm going to tell the application that it needs to load the Parsl conda environment. So there is the script that I've written. It's called setup Parsl test environment. Think of it like it just activates a conda environment. And I will ask it to execute a Python script for us whenever this application is involved. So I'm going to call that script execute Parsl task.py. And the script basically has to do a few sequence of things. So what it will need to do is it will need to read a serialized function and params package, which is written into the shared file system. So it will need to read that. It will need to deserialize that function package, execute that function package, and whatever results come out of that, we need to serialize those outputs, and we'll write it back to the shared file system. So that is what is going to happen. So this bit, so serialized function gets read into the execute task, gets executed, you get the results, and that is serialized and then written out back to the shared file system. So that's what I want execute Parsl task to do. So let's quickly see how what that method looks like. So I've got this little little script here. Now, first things first, it imports from the high throughput executors processor worker pools execute task method, and all it does is, given a serialized buffer that contains the function and its params, it will deserialize it, it'll execute it safely, and it will give you the result back. So what I'll do is, first I'll give as an argument to the script, I'll give it the name of the package, the file that contains the function package, and as the output, I'll also specify the full output path to which I expect the outputs to be written out. So that's what is happening here. So I'll read in the name of the two files that one it will read from and one it will write out to. And what I do here is I read the input file, give the buffer to the execute task method, get the result back, and assuming there are no exceptions, let's assume that there are no exceptions anywhere, no failures allowed in this demo. So I'm just going to say that at the end of it, we take that result and give it to the serialize method that again comes from the Parsl serialization library. So it will serialize the result buffer. It serialize the result to get a serialized result buffer and write that out to the output file that we, again, told the script to use. So that is exactly what is happening here. So when I register this application, so that when Balsam is told, go execute this application, it will be calling that script. So the next step is whenever we have a task that is getting launched inside a Parsl, we want that task to go to Balsam and get executed with that application profile that we just created. So I've got this launch Balsam task Python function, and it will take the function name, it'll take the task ID, it's just convenience. But the key bit is that it will take the function package, that's a path to the to where the task package is written out to on the shared file system. Similarly, the result package is where like it expects the output to be written back to. And what it'll do is it'll create a Balsam job. This is the equivalent of a Parsl task. So individual Parsl task basically gets executed as single Balsam jobs. I'm specifying the application as execute Parsl tasks. So I'm calling this definition that I just defined up here. And then I'll tell it the args to this script are going to be -i, function package, -o, result package. And what I do next is I also wrap it in this convenience wrapper called feature task, which will kind of give it a feature-like result back, though it is not really compliant with the concurrent features library, but it still gives you a sort of like a feature back. It makes it easier to pull the status of the job after it's launched to Parsl. So piece part's done. We have already figured out how to submit the job, submit a COBOL job, create an application profile, and launch a Balsam task, Balsam job through Balsam. Next thing is, if we have launched a Balsam task, we need to be able to figure out what its status is. So how I do that is through this simple function called task status poller. So here what I'm doing is I just give it a list, a job list. I give it a kill event because I'm going to try and make this a thread so that it doesn't block anything. And then what I do is I have a while loop that waits until the kill event is set. It just loops and loops. And for every job in the job list, it will check if the job is done. So you can basically do job.done because it is returning a future task object from Balsam. So here, all I'm going to do is I'm going to mimic this. I'm not really going to run it. I'm just going to activate these bits. Okay. It's all activated. And I will run this. So what this will do is I'm going to give it 2 blank features. So this is fake. I'm just going to give it 2 blank features. All of it is doing is just it will poll a couple of times and it'll print out the status of the features. Again, this is not really doing anything much. It's just making sure that the code really works. So I'm not going to try and call these specific bits and test them out because it takes a while to get a job on theta. And if I were to wait for it, it will take a while and it will slow the rest of the demo down. So let's get to step 5, which is basically now that we have the piece parts to make an executor, talk to the Balsam system. We have all the piece parts for the Balsam system. Let's put it all together to make an executor. So in the first bit, I've got a skeleton here of a Parsl executor. So I'm going to call it the Balsam executor. And I'm going to make it inherit from the no status handling executor. All that is doing is it's a very thin wrapper over the concurrent features executor class. Just to make it more Parsl, it does a bit more extra stuff. I'm going to also use this representation mixin just to make it print the executor object print better. That's it. So the init is going to take a few items here as listed here. So it's going to tell, you can tell it how many nodes do you want from Balsam, how much wall time you want it to request, a work to which you will write the input packages and the output results from the to go between the Balsam and the Parsl systems. And I'm also going to then have a couple of other methods, which I'll explain a little bit more detail. So I'll have this update task status method, which is going to update the Parsl futures, update the system with the results. A task status poller, which is again going to do what exactly we did up here. It's basically going to be a poller loop, which is going to wait for the status of the jobs. I'm going to have a start method, which is called when the data flow kernel.load is called. So when you create the executor, it isn't activated, it isn't running yet. It's when you call start that the executor actually starts in earnest. So we need it to basically create the workers, create the threads, talk to Balsam, and do all of that. So shutdown is basically just going to do a clean shutdown. Submit is another key bit. It will take the function and the args, and it'll talk to Balsam and submit that as a job. Scale in and scale out can be ignored, and scaling enabled is by default set to false for this case because we don't want to get into any extra features. We want to just do the distilled bare bones core of what an executor is. So let's start programming this. So I'm gonna start with showing what happens in start. So I'm gonna first do os.makeDirs, and I'm gonna say itself workdir must be created. I don't care if the file already exists, that's fine. Exists okay is equal to true. And then next step is we want to make the task status poller run. So right now the task status poller is blank, but I just want to create a thread and make that work. So I'm going to say self.poll thread is equal to thread, and I'm going to say the target is self.task status poller, and as args to it, and I'm going to give it the kill event that we just defined up here. So this is so that when the shutdown is called, we can set this kill event to tell the poller thread to die. Okay, and because we just created a thread, we need to make sure that it's actually started, because until you start a thread, it's not really doing it. So you need to say thread.start. Okay. So next thing is we need to register the Balsam executor. So the Balsam application profile, so that's up here. So we need to register with Balsam. I just realized that the scrolls must be difficult when the screen sharing is on. Sorry about that. And also, after the registration is done, we still need to tell Balsam to launch the job for us. We needed to talk to Cobalt and give us a job. So let's do that here. So Balsam submit job also takes a couple of options. It takes nodes, and the nodes is going to be just the number of nodes that is defined in the init. So nodes, and wall time is going to be self.wall time. Okay. So that should basically do it. So now I'm going to just comment this out, because if I accidentally start this, it will submit a job to Balsam and it will take forever to get it. So get it through the queues essentially. So that's what start needs to do. Next, let's do the submit call. Okay, this is going to be the heart of this whole thing. So the first thing we want to do is we want to create a UUID, a task ID for this task when we receive it. So let's say string UUID.UUID4. That'll give us a nice unique identifier. And then I'm going to say try accept. Okay, I'm going to assume that this is never going to happen. It's really great. So try. The first thing we want to do is we've gotten the function and its params, and we need to write it out to disk so that we can pass it off to Parsl. So I'm going to say with open. Okay, actually, we need to first serialize this. So the serialization method is this thing. So pack apply message basically will take your function, its args, and give you a buffer back. So pack apply message will take the function, the args, and the quarks, and will give you a function buffer back. Now, we need to also figure out what is the path to which we want the task buffer. Let's call this task buffer. The task buffer to be written out. So let's call this the task package. So this is the path to which we are going to write this buffer to. Okay. So we are going to write it to self work there, because we just made sure that that directory exists. And I'm going to call it function underscore name followed by task ID. and .pickle as the extension because it's a buffer. It's a serialized buffer. And let's also make the result package path because that's what we have to pass to the Balsam job to figure out where it should write the outputs to. I'm going to call it .out.pickle. So now let's open this file. So let's open this file and write out to it. As write binary as f, and we'll f.write the task buff. Now that we have written it out, we can basically pass this off to the Balsam job. So where is that? How do we do that? So we created this method, this convenience method. So I'm going to use this. So what this will do is it will create a task that will read from the task package path that we just written out. So the function name that it's taking is function underscore name. I call it TID, I believe, TID. And the task package is a path at which it should read the package from, and the result package is where it should write out. And let's also see. So this is going to give us a Balsam feature. Because it's not conformant to the concurrent features library, I'm going to do some tricks to make it work better. So I'm going to save this in, let's just make sure that there is a tasks table. Okay, so I've created a task dictionary inside the executor. So this dictionary is basically going to track the status of all of the tasks that we have launched from this executor. So I'm going to say tasks of TID, and I'm going to give it the Balsam feature. So that's going to be Balsam feature. And because it's not really conformant, I'm going to create a different feature that we'll give the user that will give out of this interface. So I'm going to just create a feature. So this is just straight from the concurrent features library. So from the concurrent features, I've imported feature. So I'm just going to create a raw, very basic feature. And that's what I'm going to give back. So let's also save the paths that we are expecting. Task package path is task package. Result package is expected at result package. Okay, so we've got everything that we need to put into the tasks table. So remember now, this submit when it's called, it is going to get the function and args. We're going to serialize it, write it out, give it to Balsam to execute. We have created 2 features, and one feature is going to be what we going to return back to the user. So we have to return this back. So we have got to return self._tasks TID, and we're going to return the Parsl feature. Now, we've launched this, but we want the thread that is sitting in the background to update the Parsl feature when the Balsam feature says it's actually done. So let's do that bit. So that's going to be the task status portal thread. So what do we need to do here? We basically need to say, we need a loop here. Okay, actually, let's copy some code from above. It's easier. Okay, so it's this loop that we need to run as a thread. So while the kill event is not set, meaning the executor is active and alive, what we need to do is we need to say, for task ID in self_tasks, if self_tasks of task ID, so we put the Balsam feature here with this key Balsam feature. If this is done, we can basically update the Parsl feature and tell the Parsl feature that, okay, the Balsam feature says that it is done, which means the real thing is done. Let's tell the user that, you know, the task that he launched is done. So let's call a method. Let's say update task status. So let's give this method the result path where the result is expected. So we still haven't read in the result, so that is still pending. So we need to tell this method to go read that and update the future. So result package is the comma, and you need to give this the Parsl future to update it. So, okay, so that's what it needs to happen. Okay. Now we also ideally want to remove this, because once the task is done, we don't need to keep polling it again and again. So let's also add that to remove is a list, and I will say to remove task ID, because now the task ID is done because it met the done criteria. Okay, so once this for loop finishes in every polling round, what do we need to do? We need to say for TID into remove, we need to remove it. So we should say self_tasks dot pop. So let's be safe and say, okay, if it's available there, if there's some, let's just have it pop out. And here, what I'll do is I'll also print polar to remove, and let's just print this out every polling period just so that we know what is going on. So to remove, this is mostly going to be empty most of the time. And let's also add a print statement here to tell us what is going on. So polar, this is going to print, let's say, status. So what it's going to do, or what it should do, is it needs to iterate on every task. So for TID self_tasks, what it should do is self_tasks of TID, and let's print the done statement. Okay, so that's what it does. I think that is right. Self-task done. Okay, okay. So that print statement I think is correct. Okay.
You need a brackets on. Done is a function call.
Not for this thing. Not for the Balsam feature. Which is again why it's not conformant with the standard future interface. So yeah, so it's just going to say done, and that's it. Okay, so it's okay. It's going to call update task status whenever Balsam says that it's something is done. We need to actually do something about that. So we need to read the result path. So with open, so let's read that. Let's open that result path. So result path, and let's read this as a binary file as f, and f.read, that'll give you the whole buffer, and let's deserialize it. So we have this method called deserialize that comes from the Parsl library that will do that for us. So let's just do that. Deserialize. Okay. And what do we get back? We'll get the actual naked result back, and we can use that to set the Parsl feature. So dot set result. Again, Ben showed how to do this yesterday. Parsl feature dot set result. That'll set the result. Okay. So I think I've got pretty much everything done. So init is there. We've got a task status polar. Start will call the poll threads. It will start the executor. Okay, let's also activate the batch job. The shutdown is, let's do a shutdown also. What do we need to do? We need to set the kill event. Kill event dot set. So whenever shutdown is called, it will shutting down, okay, and it'll set the kill event. Submit is set. Everything is written out. Okay. So how do we plug this in? Now the beauty of Parsl's config system is that we've just created an executor. We can create that executor. Let's print it out. Let's be safe and print that out. Balsam executor. I hope I did not make any mistakes. Okay. Okay. So it printed. So no obvious syntax issues, at least at this point. Okay. So I've created this Balsam executor in a Jupyter notebook, and I'm going to plug that into Parsl and run with that. So I've got this config where I'm specifying as executors. I'm going to give it the Balsam executor. So again, when I clear and load the config, that's when the Balsam executor start method is called, and that's when everything gets like created and instantiated. So when that happens, oh my God, I didn't put a sleep. Okay, bad. I should put a sleep here. I should say time.sleep poll, because otherwise that's what happens. The poller is going to go crazy. It's going to run so fast we can't keep up with it. Okay, okay. So let's kill the job. Okay, so see what happened when I just clicked that. Balsam went and talked to the scheduler and got us a job. So I'm going to kill that job because I don't want it. The Cobalt system only allows one job at a time. So I'm going to say qdel to kill that job. So now that job is gone. And what I'm going to do is go back up, restart the system. Okay. Oh, no. Okay. I think I have to restart it because the thread won't die. Okay. Sorry about that. I should have tested it before. Should be taking it. Okay, let's run this bit. Okay. Shift enter. Okay. Activating everything. Up. Okay. So reloading the executor now. Okay. So we should be expecting okay, so it's the Parsl.load is taking some time because it's waiting for a job to launch through Cobalt. So we just launched the job. So you can see we just launched a job over Cobalt. And now what I'm going to do is I'm going to create a couple of standard Python apps. I'm going to say I'm going to have this double app. I'm going to have it launch a couple of times here. I'm going to print out the futures. See, standard futures come back. Oh, shoot. Another minor error because I asked this Balsam future. Okay, wait, is that? Yep, okay, that's right. I think I might have to repeat that. Maybe I shouldn't have gone for the print statement. It's too complicated. Restart and clear because the thread otherwise won't die properly. And okay. Let's just make sure that I use the right task status poller. Yeah, okay, it's that. Task status poller. Okay. Okay, let's. Third time is a charm. Let's see if that worked. I'm going to check if the Cobalt job gets launched. It's still waiting, so it's looking a bit more positive. Okay, I think it launched. Okay, the Cobalt job got launched. I'm going to create this thing, two Parsl apps. I'm not going to use the platform. I'm just going to do double. Launch the double, print the futures, and see. It looks like the poller has recognized that there are 4 tasks. So it's saying false, 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 because none of the tasks are actually running. And there's nothing to remove because actually none of them are done. Now, I can do the normal thing and just wait for this result. So I could say for I in futures, future side.result, and it will block there. So now that cell is going to block until we get a job from Cobalt. And it looks like the queues are more kinder today, and our job is starting. So it's saying starting here. So we can wait here for like a few more minutes maybe, and it will get done at that point. Hopefully, assuming there are no other bugs that I did not spot. If anybody has questions while we wait, I will be happy to take them.
Hey, Yadu, this is Mike. This is kind of cool. You went kind of fast for me, but I was kind of wondering about, just in some of your earlier pictures, the relationship between the executor and the provider here. What provider is being used in this chain?
Right, in this system, we are completely ignoring the provider.
Okay, so you're just
because in
Balsam through the executor. Got it.
Exactly. So, okay. For example, like the threads that comes from Python are a legit executor, right? You give it a Python function, it can execute it. Similar to that, we treat Balsam as a system that already has providers built in, or it is not necessary to be implemented as a separate component because the executor itself is capable of doing all of the handling.
The stack stops there, basically, in the Balsam case.
You just need the executor.
Okay, well, if you would entertain a question on that figure that you just showed, though.
Sure.
It's not relevant to the Balsam case, but just relevant to the structure in general. No, the other figure, the general Parsl figure.
Okay.
Yeah, I'm just wondering about the interface from the executor to the providers. When you're running an MPI job and it needs multiple nodes at one time, is it asking the provider for all the nodes at once so that the provider could, for example, get a batch of nodes from the cloud, or is it asking for them one at a time, kind of like Swift providers did?
Right. So this is basically defined by the behavior that is set through the config. So you could tell in the config that I want to request blocks of n nodes, like thousands of nodes or hundreds of nodes, or one node at a time. So the granularity of the number of nodes that is requested is determined by the configuration that you set, which tells the provider what unit it should request nodes in. And then you tell the executor that you talk to this provider, which you have already configured.
So is it fair to say then that when you're just scaling out on MPI jobs, it can request the entire block at one time from the provider?
Exactly.
But if you're scaling out on single node jobs for this other use case, if you're scaling out on single node jobs, does it batch anything up to the provider, or does it ask for them one at a time?
It still expects the user to provide what is a unit. So you can just, so whether it's single node or multiple, say MPI jobs that take 4 nodes at a time, it's the unit that you tell the provider. And you can tell it like, I want blocks of 4 nodes or hundreds of nodes. Like we don't do any aggregation of requests. So if you say your granularity is one node at a time, we can't do something like, say there are thousands of single node tasks that are requested. We don't bash them together into one large provider request. So we don't do that.
Got it. Yeah. Okay, that all makes sense.
I think that is the question that you were asking.
Yeah, that is. Yeah, perfect. Thank you.
So let's just quickly check if it ran. Let's go down. Okay, it was here. Oh no, update task status is missing. Oh no. I called it update task status instead of calling it self.update task status, I think. Okay, so okay, yeah, that's a mistake there. Okay. So I'm not going to try running this again. I'll show you another notebook where I ran everything and it worked. So it basically does the same thing. So you call update task status, and at the end of it, you basically get things to update with the results like this. So, so does anybody have any more questions or anything